Start. Hello and welcome back to differential equations. Glad to see you all in class. And you won't be missing any classes in the future. Now, the section 3.3 on homogeneous equations with constant coefficients will have the equation that looks like a y double prime plus b y prime plus cy equals to, for now, 0, because it's homogeneous or homogeneous, whatever way you want to pronounce it. And we know that we said we can transform, so a, b, c are constants, hence the constant in the title. Now, the way to solve this was we create what we called characteristic equation, and that is ar squared plus br plus c equal to 0. And the characteristic equation will have 3 possible types of answers. So I am going to do that, I guess, color-coded, right? So it can solve as R1 different than R2 both real. And in that case, we have a solution that is given as y equals C1 ER1T plus C2 ER2T. So this would be our case 1, which we covered last week for the first time. And then last class, we also talked about the second case, which would be, let's go purple in this case now. This case would be the R1 equals R2 equals R, also real solution. I'll put this in parentheses. And the solution for this one was y equals C1 e to the RT plus C2 t e to the RT. The case we are discovering today, and I am going to leave this now blank and fill it in later, is going to be the case, I'll go green over here, where R1, R2 are complex. So this is what I need to cover today. So we have the 3 possibilities. I will put the barriers there. We can call this case 1, case 2, case 3. Now, in the last lecture, we learned that the number of solutions depends on the order of the differential equation. The order of differential equation is 2, so we are expecting 2 solutions. If the order of differential equation is, let's say, 5, we will have 5 solutions. And some of those solutions might be real, some of those solutions might be complex, right? Well, for odd derivatives, you must have at least one real, right? Because complex solutions always travel in pairs. That is worth writing down. It's actually better to be written in 3.2 than here, but complex solutions always appear in pairs. So you can have 2 sets of complex solutions and just have 4 complex roots. What you cannot have is 5 complex roots or 9 complex roots. You can't have a odd number of them, right? So any even could be purely real, purely complex, or the mixture, where the odd ones must have at least one real, and the rest, they could be complex, they could be combination of real and complex, or it could be all real, right? So that's for the odd roots. Now, to solve the equation AR squared plus BR plus C equals to 0, If you are able to factor, go ahead factor, and that's the fastest and way to solve these things. But most of the time in differential equations, you will have to crank the quadratic formula. Another little bit more annoying way is to do completing the square. Now, you might be that exceptional person who does completing the square in an instant. Fine, go ahead. But you will have to use either completing the square or you will have to use quadratic equation, where most of the people go to quadratic equation. So we are looking into a quadratic equation R1/2, meaning you are getting both solutions with the same equation, is negative b plus minus square root of b squared minus 4ac divided by 2a. This is the equation that we are going to use to get our r's. The solutions are going to be either 2 distinct real, 2 complex, or a repeated root to fit the 3 cases. So it can have R1 different than R2 real, R1 equal R2 real, and R1 comma R2 complex. For the complex, they always work out to be what we call a complex conjugate pair. So you will always get same numbers. The sign in between the real and imaginary part would be plus and minus. So that's what it means to have a complex conjugate pair. So let's take a look at an example and a type of the solution that we are going to get for complex roots. So case 3, R1 comma R2 complex. Now, just want to see if they're using A and B in the book. Are they using A and B in the book? Yes, they're using A and B in the book. If the solution are complex, that means that R1 will be of the form A plus BI, and R2 will be A minus BI. This is known as the complex conjugate pair, and the complex roots always come in pairs. So this will never be anything different. We'll call this complex conjugate pair. Complex conjugate pair. So now what do we do here? If we have a complex conjugate pair, the solution is given by y equals e to the at times c1 cosine bt plus c2 sine bt. This is the solution you are memorizing, and this is the solution that goes into our chart up here. That's the solution that will go right there, right, to fill in the chart. So you are memorizing this is a solution, this is a solution, and the complex one with sine and cosine is the third case. You can get any of these cases as a solution to your differential equation.
Just scroll down.
Of course. Free of charge.
Can you scroll up just like a teensy bit? Just the line before.
Sure. I did. You can see the word pair now.
Okay.
All right. So I am going to pick up an example of this. Let's say something that it's, I hope this one. All right, so we're going to start with let's see, hopefully problem number 6 would do. Y double prime plus 5y prime plus 5y equals to 0. We are going to create characteristic equation r squared plus 5r plus 5 equals to 0. From there we see that we have the, well, this is now a equals 1, b equals 5 and c equals 5, but those are the a, b, and c for the quadratic formula. Those are not these a, b, and c for the solution. So yeah. We need more letters, right? Because we are recycling. All right, so R1/2 is going to be what? Negative b plus minus b squared minus 4 times a times c divided by 2a.
But wouldn't that...
Negative 5 plus minus square root of 25 minus 20 is 5. And this one is not working. Yeah, it's not complex. Well, such is life. We got two distinct real roots. Therefore, the solution for this is y of t equals to c1e to the negative 5 plus root 5 over 2t plus c2e negative 5 minus root 5 over 2t. That's the solution. I know these are not what you would call nice numbers, but hey, stop discriminating. This is called general solution. This was a case 1, so I'm looking for case 3 example. That's okay.
Just make the a larger than big.
Yeah. So let's see. Well, a times c, right? Y double prime, this is problem number 8 now. Y double prime minus 6y prime plus 13. Y equals to 0. Gives us characteristic equation r squared minus 6r plus 13 equal to 0. Gives us r1/2 as 6 plus minus square root of 36 minus 4 times 1 times 13 over 2a, which is over 2. 6 plus minus square root of 36 minus 52. Negative 16. Beautiful. Divided by 2. And here is our complex number. Those of you not remembering how to deal with a square root of a negative number, that's what produces the complex values. You are supposed to break the square root of negative 16 into a square root of 16 and the square root of negative 1. Square root of 16 is 4, and the square root of negative 1 is I, which is how we get 4i. So we are going to have 6 over 2 plus minus 4i over 2, and that will reduce into 3 plus minus 2i. You see a complex conjugate pair because there's just a plus and minus in between real and imaginary. Therefore, we have the complex roots. And this is where we say a is 3, b is 2 to plug into our solution. Y of t equals e to the at, so that's going to be 3t, times c1 cosine of 2t plus c2 sine 2t. And that would be the general solution to the problem. When we have complex roots, this is the topic for today. So now we are going to introduce a little bit more about complex values to see the different representation for the same thing. I just want to make sure that I am not missing anything. No. So now you know all three cases. All of these generalize to higher degree, and I am going to just say higher order. And say that we again have either all the roots are real, or there is a mixture between the real and complex, and then also we have the repeated ones as well. So higher order DiffEq's constant coefficients in a title. Constant coefficients, that's important, because as soon as we start using functions and stuff, this doesn't hold anymore, right? This is just a one type, one particular type that works. So say roots are, and this is one of my favorite problems on the test. I'm not giving you equation, I'm not giving you anything to solve in this problem. I just give you a whole bunch of roots and I just say write the solution. Here are all the r's, right? I'm giving you all the r's, so no factoring, no quadratic equation. I'm just giving you r's, and you are supposed to write the solution looking at r's. So say roots are r1 equal to 3, r2 and 3 are 2 plus minus 4i, and then r5 and 6 are both 9, whatever.
What about 4? R4 and 5.
Yeah, r4 and 5, there we go. I gave you 5 roots, and this particular problem contains all of the roots. Please understand that I can actually create this as an equation, because I can just bring these roots into the binomials, multiply everything out, and give you the equation to solve. When you start factoring and doing the algebra on this, you will eventually get these numbers, right? This is how we create. This is how we create problems, right? Just start with the solution, multiply it out, and call it differential equation. So, what is the solution here? Well, immediately we write the solution. Y of t equals C1 e to the 3t. So that is your R1 solution. Plus e to the 2t times C2 cosine 4t plus C3 sine 4t. And that's the solutions from the complex. And finally, plus the solution for 9 would be C4e to the 9t. And finally, plus C5 t e to the 9. Very good. It's a very long solution, but we had 5 roots. And this particular problem had all 3 cases in one, right? We can actually work this backwards and figure out what the differential equation is, simply. Those of you who would like to practice, I'm just going to give you the way to create a differential equation. You will have to multiply r minus 3 by r minus 2 plus 4i times r minus 2 minus 4i. All of the i's will cancel because you're multiplying conjugates. And then times, I'll put it here, r minus 9 squared. There we go. If you are to multiply all of this, you will come up with r to the 5. And then remember, you just replace r's with y prime, right? Well, r with y prime, r squared with a double, with a second derivative, r cubed with a third derivative, and you will have the fifth derivative differential equation. You will know, right, that that's the equation. And that's exactly how we create these things for your textbooks, homework, exams. Right? We start with the solution.
Neatly unpacked.
Hmm?
Just so it gets neatly unpacked.
Yeah. All right. So now that we covered all of the cases together and you have them all in one spot, we're going to take a look at a little bit about these complex numbers. It's in the, we're just going to talk about the basics. Some of you already know, some of you don't. So let's just, bring everyone to the same page. Complex stuff. First of all, it's contradiction in terms of what the name is and what it actually does. Complex analysis is making a joke out of calculus and real analysis and so on, to the point where in a graduate school, if you are supposed to do a proof or something in a real analysis course, they specify in the parentheses you are not allowed to use complex variables. And the reason is complex variables work in higher dimensional space, and because they have more dimensions, there are more degrees of freedom, and everything is necessarily much easier to deal with. I like to introduce the talk of dimensions and why is that so by using the analogy of a prison. In order for us to contain a prisoner, we have to contain that prisoner in a third-dimensional room because the prisoner is third-dimensional being, let's say a human, right? So you will have a floor, ceiling, and 4 sides on the side, x, y, z, so third-dimensional. But to catch a 2-dimensional being, all you need to do is to draw a circle around or a triangle or a square, right? So if I have a 2-dimensional being, there we go, right? And if I want to put this into a prison, all I need to do is to do this. Can't go anywhere, right? Where the third-dimensional being, if you just draw the circle on the ground, you can just walk over it right out.
Depends if it's slug
Right.
and salt. If you draw a circle on a slug with salt, then it's not coming out.
Yeah, sure. So now, hopefully we understand that providing more dimensions, right, gives you more power. We start with the number itself. When you talk about number 2 is a value on the x-axis, right? So that could be considered a length. From 0 to 2, it's 2 miles or whatever, 2 inches, whatever. So you have now concept of a length, and that's one-dimensional when I say 2. But if I give you 2 plus 3i, that number brings in the imaginary axis to the table. It becomes a 2-dimensional number. If it's a 2-dimensional number, well, clearly it's the higher order creature than just number 2. Another bad thing about complex numbers is that they are calling it imaginary axis, like it doesn't exist or something. Wrong. Complex numbers, imaginary numbers, even though they're called the bad name, they do exist. Square root of -1 is defined as I, right? In a good old days, when Euler was toying with these things back in 1700s, there was no use or practical application for a complex number. So they said, yeah, just by defining square root of -1 is I, he practically doubled the existing mathematics instantly, because the good old problem of x squared plus 1 that could not be factored now can be factored. So technically just doubling everything in existence. It wasn't until 1800s, late 1800s, when Nikola Tesla used complex numbers to create alternating currents, which we are using today. So it's not imaginary in a sense of the word imaginary that it doesn't exist or something like this, because we would not have electricity in the way we know it today, right? Alternating currents. Direct currents have nothing to do with it, right? But direct currents are really bad. They are highly deadly. That's why you do not find voltages over 12 or 24 at most for direct currents. They kill instantly. You can get shocked. Here it is, 220 volts in Europe, numerous times. It could explain my behaviors and opinions, but I'm still alive. You cannot survive 50 volts of direct current. There's no way in hell you're going to survive 50 volts of direct current. So, well, yeah. But in case that it's like a car battery of two of them put together, it's way over what you need. So, guys, you have to understand that the complex numbers are not imaginary, unreal stuff, and so on, even though the bad words as real axis and imaginary axis are used. So now, when I talk about complex numbers, some of you would remember a problem in Calc 2, e to the x sine x dx, which took about a page to solve. You had to do integration by parts twice, and then you had to move the term to the other side and then divide both sides by 2. If you want to see that stuff, just go back to any of my Calc 2 lectures that are on trigonometric integral. I call it the evil problem, right? And every of my lectures has it. It's part of your homework and of the book. It's also done in the textbook. Now, again, depending on how large you write, it's either going to be half a page or a full page with 2 integrations by part, plus the trick that you might not remember to solve it. What is complex variable going to do with this? Make a joke. We are going to need at most 2 lines, and I'm going to have 2 lines because I want to write out everything, but 1 line should be enough to solve this with complex numbers. So the first order of business is to rewrite this as e to the x, and then your sine x is e to the ix minus e to the minus ix over 2I dx. And as you can see, you have, now you kick 1 over 2I outside, because that's a constant, and you multiply e to the x into each one of these, so you will just have e to the x plus ix minus e, don't need to squeeze it there, just move it here. Don't try this at home. X minus ix dx, because I'm writing out every step. 1 over 2I, you can rationalize that, multiply by I, top and bottom, who cares. Integral of, and now you factor out x, you get e 1 plus I times x minus e of 1 minus I times x dx. Hey, that's the integral e to the ax. That's a joke, right? To integrate e function. So integral is 1 over 2I e to the 1 plus I x over 1 plus I minus e to the 1 minus I times x over 1 minus I plus constant c. I did basic algebra and basic integration. In Calc 2 for this problem, well, here, I can actually, here's the Calc 2. We go into integration by parts.
Calc with a K, it's a Saturday class.
Yeah. There it is. The evil one. So, okay, this one was e to the x cosine, not a big deal. So this is what it takes to solve it, right, using two integration by parts. So instead of having any advanced methods, right, we use the basic integration technique with the e. So complex variables are insanely important because they provide us with the tools to just rip through some content of calculus easily without too much work. Complex functions are four-dimensional because you have a two-dimensional input and two-dimensional output, right? If you feed a complex number in, that's two dimensions in, and you have a complex number as the answer, well, that's a two-dimensional output. So altogether, 4 dimensions, right? That's way more powerful than single x in, single x out, or even in calculus 3, x and y in, and a single z out. That's 3D, right? So a lot more can be achieved with these functions. And math obviously doesn't stop there. I mean, today we have hyperdimensional numbers. Go out and look that up, right? Complex numbers are just 2 dimensions, right? Real and imaginary. It's a 2D number. Take a look at the hyperdimensional numbers. See what they do, right? Now, why are we talking about this? Well, the equation that I gave you here, which is the link between sine and ease, is the equation that they're talking about in the book, and it's one of the most famous equations of mathematics. If you're a math major, this is, and you are into tattoos, this must be one of them. All right, it's, yeah, that's given. So e to the I theta is equal to cosine theta plus sine theta. And for these equations, you can come up with cosine theta is equal e to the I theta plus e to the negative I theta over 2. There is no I in denominator for cosine. For sine theta, we have e to the I theta minus e to the minus I theta over 2i. So sine does have I. Probably you also know about that very famous Euler equation where you have e to the I pi plus 1 equals 0, yeah, right? So that equation is just this equation computed at pi. So if you have seen that before, yep. Note, theta equals pi, e to the I pi is equal to cosine pi plus sine pi. Well, e to the I pi is equal to cosine of pi is negative 1 plus 0. And this is where you get e to the I pi plus 1 equal to 0. This is the best math equation ever written because it contains all of the mathematical constants that are the most important. You have e, I, pi, then you have 1 and the 0. Right, 1 is the multiplicative inverse, the 0 is the additive inverse, and all of these kind of things. So
it's supposed to be e to the I pi minus 1, because it would be sine would equal.
No, plus 1.
It is plus 1? Okay.
Because when you move the minus 1 to the left, cosine pi is right. Cosine pi is negative 1 when you when you dip in the at pi in the middle. Cool. You can buy T-shirts with this. And it's really cool. All right. So now going back to what we have before, we are going to take a look at our oops, guys, plus I sine. I think I managed to. All right, good. I sine. There we go. Because that I cancels the other I, and okay, good. There we go. You see that this one does not have I in denominator, this one does, and that I is the one that cancels this I. So make sure you have it there. I dropped it also here. But the reason why it worked out to be correct is because sine of pi is 0, so I times 0 is 0. I dropped that I there, and that's an issue. All right, that's called Euler's formula. And we can express our solutions now also in the exponent form, or we can express them in the polar form. Now, polar form is the one that I gave you with the solution, with the e to the I theta. So, polar form, I don't want it blue. We have complex number z, x plus I, y, can be represented as re to the I theta. Now, before you go nuclear, let's just take a look at the simple picture, which should remind you the same way when we did the polar coordinates in Calc 2. So it's the same picture. You have some x, which is on the real axis. You have some y, which is on the imaginary axis. You have the r, and you have the angle theta. So, how do we use this to transform it into the solution that we are used to? Well, yes, you just use sine and cosine from the triangle, and you are able to convert this into whatever you want. So from this picture, right, you can write that the sine of theta is given as what?
It's going to be
Opposite?
y.
Y over r. And cosine theta? X over r. Exactly. So when you solve these for x and a y, x is equal to r cosine theta, y equals r sine theta. I'll just say it like this, and I just say flip. You know what I mean. Solve for x, solve for y. And now plug in maybe this color now, and go around and put it there and say plug in. So the z number, let's go continue blue. Z, which used to be x plus I y, is now going to be what?
R cosine theta plus I r sine.
Beautiful.
Theta.
And you can see that you can kick out this r to get you the cosine theta plus I sine theta. And now I'll write now in red, compared to no, just compared to re to the I theta. Compared to that, and from there we get that because r is r, we get that e to the I theta is cosine theta plus I sine theta. Please, next time it comes up, what's new? Someone asks you what's new. I mean, this has been around for almost 300 years, but 250. You can start with this and then see if they have any other questions. There are some other things that they tossed in here just to, do some of the mathematical flexing. We are not going to need those. Remember how I said that I will give 2 special lectures on complex variables at the beginning of that's going to happen at some point after the spring break. It's either going to be on Tuesday or Wednesday.
Monday or Wednesday.
Tuesday or Wednesday. Tuesday or Wednesday at 7:30. I'm not sure which day yet. Probably for whatever more people sign up between all of the classes I teach, including tutors and other clubs. And we are hoping to have also 2 lectures on introductory partial differential equations. Those of you going to mechanical engineering, electrical engineering, those of you going to math majors as well, you do not want to miss these if you can help it, because once you move on to the 4-year school, you will have just a preview. There are no exams, quizzes, homework assignments, or anything. It's more like a lecture of just a taste of what lies ahead, all right? But these majors are stressed because all of you will be using these 100%, right? Civil engineering is not going to use it, so, right, doesn't mean you can't show up, right? If you're a bio major and you want to go to grad school, you should be sitting in the first row, all right? You're going to have the hardest math known to mankind if you're doing mathematical biology, okay? Mathematical biology. That's the... Yeah, we beat this one to death. There's nothing else to talk about. We can just do another example and deal with this. So let's see. I want to pick something with initial conditions, right? So we have problems 21 through 26.
22.
Actually, let's go 24 to 26 because they have the third power. 22. 25.
No, I just like
Well, actually,
24.
yeah, I was now I'm going to switch to 24 or 20 because 25 you have solution on the back. I'm just kidding. 25 it is. 3y, and that's not a cube, right? That's a third derivative. Plus 2y double prime equal to 0. Y of 0 is 1. No, lies. Y of 0 is negative 1. Y prime of 0 is 0. Y double prime of 0 is 1. These are initial conditions. If you want to put this into a context of what you call a real world, because we are now sitting in a fake one, I'm just going to say, let this differential equation model some kind of a kinetic motion, where the second derivative is, we know that, acceleration, and the third derivative is jerk. Good. So we have these two concepts. Now, what are the initial conditions? Initial condition on a y, that's your position because you're starting somewhere. Initial condition on velocity, you're also starting at time 0, your velocity is 0. So, if this is y for height, well, you're starting negative 1 feet above the ground, below the ground. I mean, no, negative 1 feet above the ground is 1 feet below the ground. Oh, there you go. You're starting with a 0 velocity, and your acceleration is 1 at the start. Well, this makes sense. Just live with that negative 1 there. This is how you get to go places. Right now, in your chair, you're not getting anywhere, right? Because your acceleration is 0 and your velocity is 0. So relative to me or relative to the classroom, you're not going anywhere. It's acceleration that has to kick in so that your velocity changes from 0 to something in order to change the distance and get somewhere, right? So it's not a chicken and egg story here. Chicken and the egg evolved at the same time, right? All of these things happen at the same time, so it is a story. But anyway, let's solve this. We have 3r cubed plus 2r squared equal to 0. Factor out r squared. We have 3r plus 2 equal to 0. It's a basic algebra factoring. R squared equal to 0. That is my repeated root, right? I have two roots that are 0. And then I also have r equals to what?
Oh, negative 2/3.
Negative 2/3. Thank you. Time to put the solution together. What do I have? I have y of t equals c1 e to the 0t plus c2 t e to the 0t stiot. All right, fine. And then we have plus c3 e to the negative 2/3 t. This is what we call general solution. Now we can compute the c's. Oh no, hold on. Don't box that. What is e to the 0t?
It's just going to be
1. So,
C1 plus C2t.
yes. So c1 plus c2t plus c3e to the negative 2/3 t. That's the one that we are boxing. Good. So now we say use initial conditions. So now we're going to use initial conditions. Well, I can't really. I need two derivatives here first. So I need to find y prime. C1 just dies. Derivative of t is 1. And then I have minus 2/3 c3e to the negative 2/3 t. And I need also the second derivative because I have also condition for the second one, right? So that's going to be positive 4/9 c3e to the negative 2/3 t. There we go. All right, so the initial conditions are y of 0 is negative 1, y prime of 0 is 0, and y double prime of 0 is 1. I'm going to go like that. Each one plugs into their own. I will start at the bottom. 1 equals 4/9 c3 e to the 0. So c3 is 9/4. Are we all green on that?
Yeah.
So I used t is 0 and the y double prime is 1. You see that it says y double prime is 1. So y double prime is 1. Copy, copy, copy. And then negative 2/3 times 0 is just e to the 0. E to the 0 is 1. So all I need to do is to move 9/4 to the other side, right? And that's it. Now we go to the y prime. Y prime is equal to c2. And now the 9/4 kicks into there. So becomes 9 3/2, right? When you cancel 3/2. E to the negative 2/3 t. When I plug in, I'll say plug into y prime for c3 because and y for c3 as well. All right. So now we have this. We use the initial condition 0, 0. So that's a 0 equal C2 minus 3/2 e to the 0. So C2 works out to be 3/2. And now we have the y, which is C1, plus C2 is 3/2 t, plus, and now I have 9/4, right, because it's just C3, e to the negative 2/3 t. We plug in y of 0 equals -1. So -1 equals to C1 plus 0 plus 9/4. C1 is equal to -13/4. Thank you. Finally, y of t is equal to -13/4 plus 3/2 t plus 9/4 e to the negative 2/3 t. There's your particular solution. That's what I work for. Now go back and review this procedure 15 times and then try another example. I would like to work out one that will have sines and cosines to find C1 and C2, because I know how much you love that stuff. I don't want to get you, disappointed in that department. And I don't see any. Wow. I'm going to start bringing the other book. What did we say? So should I make up one right now? Or we can review this after the exam. Let's put it off. I'll just write it like this here in blood. Needs a complex example. Complex example with initial conditions. So we can go and do the review for some time prior to your leaving. And this is I just do this.